Let's go ahead today and talk about neural networks, and we're going to talk about generic neural networks before we get into more of the specifics, before we get into things such as convolutional neural networks and GANs, and of course the transformer model, which is the result that is taking everybody by storm because this is the this is the algorithm that's used. Okay, that's better. You notice I adjusted I adjusted my scene because my eyes are supposed to be on the top two-thirds of the screen. So we'll get into convolutional neural networks. We'll get into GANs, how they work, diffusion models, and also the transformer model. But we're going to talk today about we're going to get to it about the algorithm that's used in all of these, which is error backpropagation, which is just a genius result and a beautiful piece of mathematics initially reported, I think, if I mentioned before, by Paul Werbos in his 1975 doctoral thesis. Okay, we're going to first of all look at artificial neural networks and so-called supervised models. There's two types basically two types of ways of learning stuff. One is supervised model, where you take your data and you label it. There's other cases where the data isn't labeled and you got to look at it and you do something called clustering. I think that's the generic term that covers just about all the unsupervised cases. And unsupervised means you look at the data here and you look at the data here and you say, you know what, it looks like this data is different than this data, so I'm going to draw a classification boundary between them. And this is very heuristic, and there's no really right answer. Supervised models, on the other hand, we do have a true model that we can work at. We have an error that we can memorize, such as not the case for unsupervised learning. So let's look at supervised learning. First of all, the idea is you're given a stimulus, an input, and you have an output, the response data, if you will. And the object is to train a machine to simulate the input-output relationship. Many times you have equations to describe if you stimulate here, you get a response. Many times, though, we don't have models, yet there is kind of the assumption that there is an underlying model. There's an underlying mathematics which allows you to map the input to the output. We just don't know what it is. And so we give it to a neural network in terms of the supervised learning, and the neural network basically begins to simulate whatever that underlying algorithm is. And I'm reminded of the old movie, The Invasion of the Body Snatchers. There were two versions made, one in the 50s and then one later with Donald Sutherland. The one in the 50s is probably the best. It's black and white, but it's about these iPods and not iPods. They're pods from outer space. So there's these pods. They're about the size of a large watermelon. And you put this pod beside you because it's from outer space, and it begins to take on your features and it begins to emulate you and simulate you. And then once it has taken and simulated you, it kills you, and that simulation kind of takes over. But the simulation is never perfect. So I think supervised learning is like Invasion of the Body Snatchers. We have the model, which is the human being. We have the pods from outer space that come in and they begin to duplicate or simulate uh, the human being. And but that simulation is never perfect, is it? It isn't perfect. So if you do have math equations, you should use the math equations. You should use the models. Again, this gets back to the idea of domain expertise, and there's nothing better in domain expertise than actually a good, solid model. And that model allows you to do a lot greater things. So if you want to figure out how far you throw a ball in terms of, um, let's say, the velocity of your release and the angle of your release, and there's no wind going on, you can either throw the ball 1,000, a million different times and figure out the inputs being what? Your initial velocity and then your angle of release. And you could gather data all over the place. And you could take that data, the angle of release and and the initial speed, and you could train a neural network to actually predict how far the ball would go, right? You could, but that's kind of stupid because you have a mathematical model that you could go to. We could train it to figure out how far the ball goes, but if you do have a model, that's a heck of a lot better. So use supervised learning when you don't have a model and you're trying to emulate some sort of unknown model that is generating this data. So the object is to train a machine to simulate the input-output relationships. So, for example, throwing the baseball, the input would be the initial velocity and the angle of release, and the output would be how far you threw the ball. And if we didn't have a model, again, we could train a neural network if we had a bunch of training data to do that. So there's different types. There's classification. We're going to talk about classification first of all. Classification is discrete outputs, and you have to be very careful about classification, sort of neural networks and artificial intelligence in general, because you're going to get false alarms. You're going to get false positives, false negatives, and that's just unavoidable. So And then there's regression. Regression is when your output is continuous, like if you're trying to forecast the power load for tomorrow. Now, classification, you got to be very careful. You got to be very careful in neural smithing this. The military one time used neural networks to determine out of an aerial photograph, a reconnaissance photograph, whether there were tanks in the field. And they got all excited because they took a bunch of pictures of tanks and fields without tanks, and they used it to train a neural network, and they got this incredible result until somebody noticed, well, you took all the pictures with tanks in them in the evening. So therefore, the background was darker. And what the neural network was doing was not noticing the tanks were there. They were actually noticing the degree of darkness. So that's difficult. There was another one where there was an attempt to classify dogs from wolves. And they got a neural network, and it was really, really great. It really did a good job classifying wolves as dogs. But some smart person came in and he said, you know what? He says, all of the wolves have snow in the background because they were wild wolves. And what the neural network was doing, or the classifier was doing in general, was looking at whether or not there was snow in the background. It had nothing to do with identifying the wolves and the dogs. So you always have to be careful in your training data to make sure it isn't biased and you're trying to learn something that isn't there. We talked about the idea of hallucinations. I think that is another example of that. So we have these supervised learnings, we have classification, we have regression. All of them use labeled data, and there are cases of unsupervised learning, which kind of goes into supervised learning. So there's lots of cases where things are mixed these days, but this is the general differentiation between the two types, supervised and unsupervised. Supervised is where you label the data, unsupervised is where you don't label the data. So here's a simple example. We have a bunch of people here. I'm there twice. I'm wearing a hat in the upper left, in the middle, and in the right, in the middle. That's me too. And then there's some other people. Anybody know who this is? That's Ronald Reagan. This is a guy named Paul Harvey. He used to be a great journalist, and he was a great journalist. This is a guy named Rush Limbaugh who passed away, who was just fun to listen to. And this is James Arness, who played Matt Dillon on the television series Gunsmoke. So the idea of a classifier is to present a bunch of people like this, and the way I'm presenting it could also be shown to be a novelty filter, if you will. What you want to do is you want to have novelty filters in order to determine whether it's a Marx or it isn't a Marx. So therefore, you get a recall from the trained classifier. And therefore, if you present a picture which it hasn't seen before into the classifier, it would say Marx. The important thing is that the test image does not appear in the training data. In other words, you have to generalize, you have to interpolate among the training data in order to get the proper classification. Because if you only classify things which were in the training data, you've memorized. Memorization is not the same thing as learning. Learning means you can take concepts and you can generalize them, and that's exactly what we're doing here. Um, so here's a general view of what's happening in feature space. Suppose we have two features. We have the dots, which are pictures of marks. We have the little X's, which are not marks. And hopefully, in some sort of higher dimensional space, that there's a boundary between the Marxes and the non-Marxes. And that boundary is referred to as the concept. And what we're trying to do, you can see the concept is this white boundary here, which separates the dots from the little X's. And what we're trying to do is we're trying to find that boundary. That's the underlying truth. But we only have the data. We don't have enough to actually specify this concept totally. So therefore, we come up with a representation. This representation is um, about well, it's an estimate of what the concept is, and that's what you're trying to learn. You're trying to learn the dashed green line, and you're attempting to get that dashed green line as close to the white line as you possibly can. Just this viewpoint kind of tells you some interesting things. Let me tell you one of the interesting things. One is the usefulness of data. Suppose that you had a partially trained neural network and you knew this green line and you wanted to generate some new data. And this new data is at your discretion. You got to pay for it. It'll cost you money to get pictures of me because I charge money for pictures of me. And so you want to be judicious in it. So here's the point. If you get a new picture of me that's right in the middle here, is that going to tell you anything? No, it's not going to tell you anything. What you want is you want pictures of me that are close to the boundary or pictures of people that are not me close to the boundary. So therefore, if you're trying to do queries and you have the ability to generate your own data, and in order to fine tune your classifier, you just don't want to generate that data at random. You want to generate that data around the representation because that's where you have your most ambiguity as to what is happening. So there's some insight here. Um, and then we'll talk about some other insight as we go along from this idea. There's lots of things you can learn just by looking at this simple schematic here. So let's talk about
Dr.
supervised.
Marks,
Yes.
before we continue, I'd like to ask a question. So, is for the concept or truth, is this something that you can mathematically find, or is this something that is, once again, fuzzy? It depends on who views it and what they say is the concept or truth.
Okay. We're assuming that that exists. Now, the interesting thing is that many times this boundary is indeed fuzzy, and you are going to get false positives and false negatives. For example, suppose that you were trying to train a neural network for uh, things which were trees and things which were not trees. And so you get this concept, and then you get this ambiguous sort of result. And what would be an ambiguous result? I think it would be like a bush. A bush isn't a tree, but man, it kind of looks like a tree, doesn't it? So that would be something which would be ambiguous in your classification attempt. So yeah, many times this result is not 100% true, and you are going to have dots outside, and you're going to have pluses inside. That's a little bit beyond what I wanted to talk about, but the idea is that yeah, you are going to have that because in detection theory, you always have your detection probability and you have your false alarm probability, and you can't get away from it. Anytime you detect something, you always have a false alarm. Think about when you read media. You're trying to detect whether a something which is posted on media is a fake story. Now, if suppose that you want to have 100% detection probability, you want to detect the truth 100% of the time. If you want to detect the truth 100% of the time, you accept everything that you see on social media and post it in the news. You'll never make a mistake and you'll always be subjected to the truth. But what's the problem? You're going to have a lot of false alarms. Okay. Well, what if you don't want to have any false alarms? If you don't want to have any false alarms, then you reject everything. So you accept everything, which means you're incredibly gullible. to an extent, and then you reject certain things. If you reject certain things, you're very skeptical. So you don't want to be 100% gullible. You don't want to be 100% acceptable. So what do? You apply your domain expertise and filter out the weird results from the other results. And I don't care what you do, you're going to be sucked in. You're going to be sucked in by some false alarms and well, false positives and false negatives. So you'll never get your detection probability up to 100%. You'll never get your false alarms down to 0%. So, Riley, you're right. This is an idealized case, certainly where there is a differentiation. And there are cases where there are idealized cases. For example, where I threw the baseball, angle of release and the initial velocity of the ball. I think that that probably has a very well-defined concept, and I don't think that there's very many false alarms that you could have in training a neural network to do something like that. Okay, let's go on. Supervised regression. This is interpolation. We've talked here about classification. Now, classification is either a one or a zero. You either get a yes or a no. It's a marks or it isn't a marks. Supervised regression is when the output data is continuous rather than discrete. One of the places that we did some work in, which was really received well, is in power load forecasting, where we were approached by Puget Power, who had a guy named Lloyd who stuck his finger up and he tried to predict what the cost of the power was going to what the power consumption was going to be the next day. And basically, what Lloyd would do, I forget his last name, but he would wet his fingers, stick in the air, and just use his domain expertise to try to make his best guess. Well, it turned out Puget Power had all of this past data, so we used a neural network to train and figure out what the load forecasting was. And Puget Power adopted this. And then I think about a year later, there were 32 utilities using neural networks to forecast the load. So you do the training in, for example, with load forecasting from the historical data. And for the load forecasting, you use things like temperature. Like if the temperature is really cold and you have electric heating, then that's going to do a lot of consumption of power. You have the current load, the day of the week, holiday, etc. And then the output is the next day's load. So we have data from the past trying to forecast data from the future, and this worked out incredibly well. But nevertheless, we had to be very careful about our data. For example, we found out that Thanksgiving and some holidays were totally uh, not representing what the data was trying to do. In fact, on the holidays, we had this very interesting phenomena that the electric load went for a little while, then there was a big spike, and then it kind of trailed down. And my friend Mohammed El-Shikari called this the turkey effect. Because what do? Everybody sticks their turkey in the oven at a specific time in order to cook the Thanksgiving dinner. And so we could not use the turkey data the turkey data, the Thanksgiving data in order to train the neural network. It was an outlier and it wasn't good. So even here, you have to be careful about the data that you choose. And so this was the training, the test data, of course, once the neural network was trained. It's forecasting temperatures, current load, day of the week, holiday, etc., and it gives you tomorrow's load forecast. Even here, looking at the historical data, you got to be careful because when I was in Seattle, Puget Power, Puget Sound, by the way, is the name of the waterway near Seattle, so they call themselves Puget Power because it's nice alliteration. And we looked at the data, but it turned out that Seattle had been growing. So could you trust the data, which was 5 or 6 years old? I don't know, because the power consumption has generally increased. And how do you actually adjust for that? And there are ways in training regression machines and to take into account that your data was old. And so there's ways around it, but nevertheless, that's something that has to be recognized. Are you indeed having a stationary process? Is your data time invariant? We're all familiar with time invariant filters like FIR filters and things of that sort. And we're familiar in stochastic processes, which are stationary processes. This means that the statistics today are kind of like the statistics of tomorrow, or kind of like the statistics of the past. And when you have stationary data, you can train on neural networks and regression machines in order to give you a good answer. But if you don't have stationarity, if you have dynamic sort of processes, you're not going to be able to do forecasting. So, what are properties of good forecasting? Number one, good classifiers and regression machines. Number one is their ability to interpolate. They have to have good accuracy outside of the training set. We certainly want that. Another thing is we would like an explanation facility. We would like to generate rules after training. Neural networks are incredibly lacking in doing this thing. I don't know if I shared with you about the election of Bill Clinton. Bill Clinton, when he was running for president, he hired this hack. It was a guy that came out and gave neural networks a really bad name, um, in order to figure out bad policemen, because Bill Clinton was having his convention in Chicago. And a bunch of years earlier, there was a convention in Chicago, and there was a bunch of yippies all out trying to riot and do bad things, a lot like they're doing today. Things don't change very much. I mean, the yippies were, I don't know if you've ever heard of the yippies. They're kind of like the hippies, but they're just weird politically, and they did weird stuff. They went to $1,000 a plate dinner and gave away outside after setting up a card table. They gave away free bologna sandwiches. I thought that was kind of funny. They went to the New York Stock Exchange and took $1,001 bills and they threw it over the balcony and watched all of the traders kind of run and try to grab the dollar bills, trying to make the point that these were just greedy capitalists. So something like that. So the yippies were really weird. And when they came to the Chicago riots many years ago, they actually caused riots. There was a trial, and it was called the Chicago Seven. They made a movie out of it. If you ever watch it, it's a really good movie. It's about how these yippies work together in order to establish these riots. It's kind of like, oh, what's that? Some of the organizations today that go in and try to initiate riots. Well, anyway, it turns out that the mayor at the time was Mayor Daley, and Mayor Daley said, "Get the police out and get the police out and stop this riot. I don't want this happening in my city." And so the police came out, and some of them were overly exuberant, and they banged heads. And headlines read that there was a police riot. And it wasn't the kids that were rioting, it's a police riot, because they were actually going out and bonking people in the head. So this happened a long time ago. It was now Bill Clinton's nomination process in Chicago. They didn't want a repeat of this. And it turns out that before the mayor of Chicago was Daley, it turns out that his son was now the mayor of Chicago. So they hired this hack who was a neural network hack, just a guy that went out and misrepresented neural networks and really gave him a bad name. And what he did is he ran all of the policemen through a neural network to try to determine which ones would go crazy. And he looked at things such as domestic sort of challenges, any reports of violence while they were in the field, etc. And they used this not to fire the policemen, the Chicago policemen, but to put them on furlough. Well, it turns out that the people that were representing the police department, which was the union, took this to court, and it was thrown out of court. And the reason is exactly this explanation facility. The court threw it out, and the court said, well, this is all well and good, but why are these policemen tagged as being dangerous? And the best they could do is because the neural network said they were. And wow. So that was something the judge didn't like. He said, you have to tell me why. You just can't say the neural network did it. You have to have an explanation facility. You have to be able to tell me the reason why. Now, Pablo Rivas over in computer science is doing something fascinating. He had a grant from NSF where he was looking at Facebook posts, trying to determine things such as sexual predators and dangerous people and potential school shooters. And I'm not privy to the details of his research, but this was the basic idea. But the point is that if he did come up with something and say, okay, in Facebook, this guy looks weird, man, go out and arrest him. They couldn't do that because of the same lacking of the explanation facility. They would rather have to handle it over to a mental professional who would look at the data more and say, yeah, this person is unsafe because of X, Y, and Z. And all of a sudden, this expertise came in, and that would be legally defendable. But just having the neural network, the classifier say it was true is not enough. We still suffer from this problem. We still suffer from the lack of an explanation facility in neural networks. Um, we're going through the properties of good classifiers and regression machines. And the other one is fast training. It turns out that there are some things which are really, really fast in training, other than neural networks. Neural networks take a long time to train. That's the reason they're a big sink on all of the electrical utilities, and they're using up all the electricity because it takes a long time to train a neural network, especially a deep neural network like these large language models. And so that's not a good trait of neural networks. And you'd have to have fast testing. And what does that mean? That means that after the neural network or the AI is trained, that you can get a response relatively quickly. This is true of neural networks. If you've used ChatGPT, you can see that their large language model, their neural network responds very quickly, doesn't it? So we do have fast testing. In other words, we can poke it to get ideas, and the results are a lot more quick than the literal training. Uh, th- we're all familiar with neural networks, and there's a reason that neural networks have won out over some of these other techniques as far as the depth of their ability to learn. But there are other techniques to do this. One is classification and auto-regression trees. I wrote a paper a long time ago with some colleagues at the University of Washington where we compared neural networks to classification and auto-regression trees. And when I talked about the no free lunch theorem, it turns out that well, it turns out that what we did is valid, but the neural network only worked better than the classification trees on the problems that we talked about. There were other ones that wouldn't that wouldn't be the case. There's nearest neighbor lookup. I mean, my goodness, why not just have a bunch of data and then that constellation of data, and then just have a query coming in and looking at some sort of metric of the distance between that and the nearest neighbor in your data set. And heck, that works. But what's the problem with that? Number one, you have to store all of the data explicitly. And after a neural network is trained, you don't have access to the training data at all. And so you don't have that big memory problem. That's something that could be done, but nearest neighbor lookup is something that could be done in terms of classification, like in determining the marks. You could figure out the nearest neighbor. In fact, large language models do this, and they do this very well. They have this capability of nearest neighbor lookup. You have, for example, the idea of queen and king. They are vectors in a high dimensional space which are very close to each other. And the difference between king and queen is the sex. And so if you take the difference between those two vectors, you get another vector, which is the difference between the queen and the king. And then if you go to husband and you add that little vector in, you'll get something very close to wife. Isn't that interesting? So large language models kind of put these things together in an incredibly high dimensional space. And as we've seen with the curse of dimensionality, we have to be careful about the dimensionality of our space, but we have a good way of doing it, and we'll talk about that. Another one which was really in vogue for a long time, but I don't see anymore, is vector support machines by a Russian guy, and they talked about the VP distance and things of that sort. Everybody thought this was really, really great because there was an explanation facility and things of that sort, but they don't scale well. You still have to do a lot of neural smithing, if you will. You have to go in and put a lot of hyperparameters in there. Neural networks, of course, are good for classification and regression, and the flavor of neural networks is very wide. We have the layered perceptron, which we're going to go through. We have recurrence perceptrons, and the recurrence perceptrons have feedback. If you've taken a course in digital filtering, you know that there's IIR filters and there's FIR filters, finite impulse response. The IIR filters have feedback, right? And the finite impulse response filters do not have feedback. So that's kind of the difference between the layered perceptron and the recurrent perceptron. The recurrent perceptron has feedback. Cascade correlation neural networks, radial basis neural networks, deep convolutional neural networks, and uh, and the idea is applied also in GANs, diffusion models, and transformer models such as Grok and ChatGPT. So let's look at a model of a neuron. This was the model of a neuron proposed by Hebb in the late 1940s. And he said, we have weights coming in, and these weights are from different these are the synapse strengths. And you remember the idea that neurons that fire together are wired together? That was his sort of idea. Now, according to the Hebb's result, you summed up all of these. You summed up the state of other neurons. These Z's are other neurons, or they could be input. They could be input from your senses, such as your smell. I don't know, what do they have? Smell pods or something. And these are weighted and then they are summed. And according to Hibbs, it was just um, subjected to a step function. Hibbs was more interested in classification. He wanted a one or a zero out. Well, in general, for regression, we use something called a sigma, which is called a squashing function, and we will dictate what the squashing function is. It turns out that the you have to have nonlinearities to do anything interesting in classification. Because if everything is linear, you have linear operations of linear operations, and that's another linear operation. If you multiply two matrices together, you get another matrix, and not that's not good. So you want something that actually is nonlinear in order to allow yourself to do great things. So the sum is equal to the sum of the inputs from the other neurons or the input multiplied by the weights. And you'll notice this is a vector-vector multiplication, right? And we'll see that we have lots of vector-vector multiplications. We have lots of matrix-matrix multiplications, which is why NVIDIA is making big bucks because they're really good at multiplying big matrices together. So what happens is that this summation is subjected to the so-called squashing function, and that outputs a z. Now you notice this z is the same variable as the z up here, which means that this z might be transmitted to another neuron. Or heck, it might have a feedback. It might feed back into itself. So there could be all sorts of different things. So what is a squashing function? One of the most commonly used ones is the so-called sigmoid squashing function. Sigmoid corresponds to an S-shaped curve. And here is the definition of the sigmoid in the upper right, 1 over 1 plus e to the minus x. And if you plot that out, you get something which looks like this. And by the way, this is usually what happens when people say things are exploding exponentially, such as COVID, right? COVID was just exploding exponentially. And so right here to the left of zero, it looks like it's an exponential increase, right? But it turns out that as things got better, not got better, as time progressed, there was a leveling out. If you remember, the COVID sort of thing was talked about quite a bit in terms of the number of incidents leveling out. When is the curve going to level? So this is a very deceptive sort of curve, but that has nothing to do with using it as a squashing function. Why is it called a squashing function? Well, it's because it squashes the number. It takes every number between minus infinity and maps it between 0 and 1. So it squashes that big interval into a very, very small interval. Now, this particular curve is really cool because in error backpropagation, we have to take derivatives. And taking derivatives is really a bummer because usually you need 2 points. You do kind of a secant line between them. And if the 2 points are close enough, you do the slope. And that's the first derivative. But let's look at the sigmoid function. This is really interesting. The derivative of the sigmoid function with respect to x, if you use calculus, is this. You'll notice that there's a 1 over 1 plus e to the minus x in here. In other words, embedded in this equation is this equation. So we're going to suck that out, and this is what we're left with. But this turns out to be 1 minus the sigmoid function. So the derivative of the sigmoid function, you don't have to take the derivative. It's equal to the derivative, it's equal to the original sigmoid function times 1 minus the sigmoid function. That turns out in error back propagation to be a very big deal because we don't have to take literal derivatives. And you're not familiar with that right now, but we will see that. Another one that's used quite a bit is a hyperbolic tangent, which is kind of a sigmoid stretched out along the y-axis. And if we use a hyperbolic tangent, this is also a sigmoid function in the sense it has an S shape, if you will. Well, its derivative is 1 minus the tangent squared. So the derivative is 1 minus sigma squared. One that's used quite a bit these days is I call it a half-wave rectifier. It's 0 for negative values of x, and then it goes up linearly after that. It's really not a squashing function at all. It's something else. So let's talk about error or loss. It's called the loss function. And it turns out there is going to be an input vector set I, and you want to map it to a target vector. So, for example, for throwing the ball, the input vector would be my angle of release and the initial velocity of my release. And the target vector would be what? How far the ball went. And then the neural network output is I sub n. So I'm sorry, O sub n is the neural output. Now, P sub n is what you want. O sub n is what you get. The neural network isn't always going to give you the tagged response. So let's look at that again. We give an input and we get an output of O sub n. But we know that the output O sub n isn't right because it should be P sub n. So again, P sub n is what we want. O sub n is what we got. And what we want to do is we want to minimize the error between what we got and what we want. And so this is the error. It's 1/2 times the what you want minus what you get squared. And we square it because, I don't know, negative error doesn't make sense. We want to make sure it's a positive error. And we put this 1/2 here for just bookkeeping reasons. It turns out eventually I'm going to take the derivative of this. And when I take the derivative of this 2 is going to hop down and eat up the 1/2, and we won't have the 1/2 to bother us anymore. So if we minimize this error, we minimize also the error without the 1/2. But the 1/2 there is put there just for bookkeeping reason. So here's minimization techniques. I think the error is a function of the fixed training data and test data, and it's going to be a function of the neural network weights if we train the neural network. And again, we want to get what we got close to what we want. So the idea is to find the weights that minimize the error. We want to find the weights in the neural network that minimize the error. And there's a number of ways to do this, and they're mentioned here. And the best one, I think, is error back propagation. It stood the test of time. There's other ones: conjugate gradient descent, random search, genetic algorithms. Genetic algorithms are really terrible. If anybody, genetic algorithm is a type of evolutionary algorithm, and it's just a terrible way of doing it. So let's look at the idea of steepest descent. Steepest descent is very important because this is, again, what neural networks and other places do. The main idea is to find the way downhill and take a step. Suppose we're trying to minimize something. We're trying to minimize, we have this, we're trying to minimize the error. And the minimum error might not be 0, and that's okay, but we still want to minimize the error. So what's a good way to minimize the error? Well, this is where we're at. We're standing on a hill, and we don't know what this bottom is. The best we can do is kind of stick out our foot and figure out which way is downhill. Well, sometimes we can calculate which way is downhill. If we calculate which way is downhill, we can take a step in that direction. And that's what this iteration is showing here. X is replaced by x minus eta times the slope. And the slope is the slope of the error function. And that will give us a steepest descent. That will give us a step getting towards the result. Uh, and so we do this kind of a step at a time. Now you notice there's something eta here. This eta is your step size. The question is, once you know which way is downhill, are you going to take a big step? You're going to take a little step, right? If you take a big step, you might overshoot. If you take a teeny step, you're going to kind of take all day to get to the minimum. So eta is a hyperparameter, one that has to be chosen by the neuralsmith, and there's ways to estimate this. And so that's the basic idea of steepest descent. Now there's gradient. There's a variation of this called stochastic descent, where you don't have the derivative, and you're on this hill. The only thing you can see, by the way, is your feet. You can't see which way is downhill. And you stick your foot out, and if it's downhill, you take a step in that direction. If it's uphill, well, you ignore it. You go back to where you were and take a step in another direction. So that's just stochastic descent. This steepest descent is more sophisticated because not only do you know where you're at, you know which way is downhill. You don't have to poke your foot around. You know which way is downhill, and you take a step in that direction. So let's take an example. Let's suppose that the error is 1 half x squared. Now, 1 half x squared has a minimum at x is equal to 0. We all agree with that, right? It's a hyperbola, and it has a minimum of x is equal to 0. Its derivative, this is the distance downhill, minus the derivative with respect to x, that's equal to minus x. So therefore, we replace x, our new estimate of the minimum, by x minus a step size times the direction downhill, dE dx. And so if we do that, since dE dx is equal to minus x, it turns out to be 1 minus eta to the x, or 1 minus eta times x, I should say. So this is your this is your steepest descent. You're at x, and then you take 1 minus eta times x as your next step because that's the way it is downhill. So this actually gives us a difference equation. We all have studied difference equations in um, digital signal processing. And the difference equation is that the new value is equal to 1 minus eta times the old value. And if we look at the solution of this difference equation, you can solve this using Z transforms, or if you've seen enough of these, you can do it in your head. It turns out that x sub p is equal to 1 minus eta to the p times your initialization. So this is the closed form solution to this iteration. Does that make sense? And you will notice something interesting, that if 1 minus 8, if the magnitude is less than 1, you take anything which is less than 1 and you raise it to a very large power. So you let p go to infinity. That turns out to go to what? It turns out to go to 0. So this term, 1 minus 8 to the p, if this thing in the parentheses is less than 1, the magnitude is less than 1, this is eventually going to go to 0. So therefore, we see as the number of iterations increases, we do get 0, which, if you remember in our original problem, 1 half x squared is where the minimum is at. So this is a simple example of using steepest descent in order to find the minimum. So let's look at something more interesting. This is a pretty cut and dried thing. Let's suppose that we had a perceptron. Now, this perceptron was originally proposed by Frank Rosenblatt, and he's a really smart guy. And it was perfected, I think, by Bernie Woodrow. Rosenblatt did some interesting things, but it was Bernie Woodrow that did things with steepest descent, which are still astonishing in the 60s. You saw the video way at the beginning of the course where he was actually able to do like voice to text translation. He was able to train a neural network to play blackjack at the optimal level. He was able to forecast the weather better than the local weatherman. So that's really kind of cool. Okay, so here's our perceptron. The perceptron just has an input and it has an output and it has weights here. So whoops, I don't know what happened to the error. The error here is equal to 1 half times what you got minus what you want squared, right? The output is the output of the neural network. P is what you want it to be. So this is the training data. So you want that to be minimized in some sort of sense. Well, let's look at the output. the output is equal to, as you can see here, the summation of k is equal to 1 times the weights times the I sub k. That was our model of the original neuron. So it's equal to the weights times the input. The input is down here. We multiply it by the weights. You'll notice that if you unpack this, this is a vector matrix multiplication. W sub nk are elements in a matrix. I sub k are elements in a vector, and we're doing a matrix vector multiplication. So this result is replaces what our output is, what we got, and then we subtract what we want. We square it, and that is the error. Now we'd like to take the derivative of the error with respect to the weights, because that's what we want to do. We want to find the weights that minimize the output error, and we're going to go downhill. So the derivative of the error with respect to the weights is equal to the equation which you see second from the bottom. And you can apply regular calculus here in order to perform that differentiation. And you can see here again, minor point why we use the 1/2. We use the 1/2 here because this 2 comes down and it eats up the 1/2, and we don't have to worry about that anymore. So this is the derivative with respect to the weights. So what this does is this tells us how we can adjust each of the weights to make the overall error go downhill, because the derivative of the error with respect to the weights tells us downhill. And so we have downhill for weight, the first weight, the second weight, all the different weights. We have the way to go downhill to reduce the error. And so what we do is we look at this error. And by the way, this error is equal to I sub j. This is for the weight mj. It's equal to I sub j. And the difference between, again, what you want, what you got. So let's go to the next step. This is the direction downhill for all of the weights, and therefore we want to replace all of the weights by the previous weight plus a step going downhill in order to reduce the entire error, in order to reduce the error between what we got and what we want. So W24 here, that's an example. All of them are this way. But I'm just choosing W24 as an example. W24 is replaced by W24 minus the step size times I4 times O2 minus P2. Where is this? What is this? This is the direction downhill, right? This is the direction downhill. So therefore, we are fiddling with the weights to make sure that the error goes downhill just according to this single weight. And we can do this with all of the weights and go downhill and hopefully reduce our error between what we got and what we want. Now, there are no hidden alters. That should be layers. And that's linear separation. That's not good. So if you just look at this very simple perceptron, it has 3 weights and a single output. And we're going to use it as a classifier. If the output is greater than a half, we're going to announce class 1, like it's a Marx or not a Marx. If the output is less than a 1/2, we're going to say it's number 2. Is that okay? So we're going to take the output, we're going to make it to a classifier simply by thresholding it as Hibbs originally did. Now, what does this mean? This means that there's a classification boundary. If the output is 1/2, we're right on the boundary, right? So therefore, we can look at the boundary, the output, and we can say, this is where we have our maximum degree of ambiguity. And on one side of this boundary, we have a type 1 classification, and the other type, we have class 2 classification. But the thing is, this is the equation of a plane. This is not good. So what happens is this neural network right here has the inability to do very much. All it can do is separate data that is separated by, in 2 dimensions, a line, because this is an equation of a line. Not only that, it's a line going through the origin. And that's not very good, because that really limits the application of this simple perceptron. And this manifests itself in higher dimensions. It turns out that in higher dimensions, there's a hyperplane which separate the 2. And that's your classification boundary. So up here in the green is classification 1. Down here is classification number 2. So one of the problems, and we can address one of the problems, is to get this thing not to go through zero, because that isn't good. That's a pretty big restriction in order for the classification boundary to go through zero. So what we'd like to do is we'd like to put in something called a bias. And the bias is just a neuron that always has a state of one. This value is always one. Doesn't matter what the other inputs it is, always has a state of one. And it has a new connection. Well, it turns out that if we put the bias there, that this is actually the offset in the line. This is the offset. And it allows us to take this line that goes through the origin and move it. Now, it turns out that the difference between the two classifications is still a line, but but at least we got it off of the origin, which is really good. Now, the people, as I mentioned before, that kind of derailed neural network research were Papert and Minsky and Papert. They wrote a book called Perceptrons. And this is what they pointed out. Everybody was doing this. Adeline, which was Bernie Woodrow's, was using this no hidden layer, uh, just mapping the input to the output, as was Rosenblatt with his perceptron. So here's what they pointed out. They said, let's take an exclusive OR. You talk about a simple classification problem. This is an exclusive OR. 0 and 0 is 1, and 1 and 1 is 0. You guys know what exclusive OR is, right? Nod your head if you do. Okay. So exclusive OR is a 0. This turns out to be a 0. This turns out to be 0. And the corners are 1. And their point is that you could not take this classification tree, this perceptron or this Adeline, and train it to differentiate to do a simple exclusive OR. Now, if you couldn't use it to explain a simple exclusive OR, how could you use it for anything realistic? There's going to be so much stuff, according to Minsky and Papert, that can't be resolved by this. The simple operation of the exclusive OR cannot be resolved using a linear perceptron with bias. And the bigger point is, more importantly, problems can probably not thus be resolved without a linear perceptron with bias. There has to be other sorts of problems. So what they were pointing out is the limitations of the neural network. Now, the thing about the Woodrow and Rosenblatt neural networks was that they had no in layers. It was directly a input to an output. So somebody suggested using hidden layers. Now, what's a hidden layer? Well, it turns out that you have an input layer. You're going to have a bias network, and then you have this hidden layer, and the hidden layer isn't connected directly to anything. And these hidden neurons don't really have meaning. We know what the input is. We know what the output is. We can give it understanding, but we really don't know what this hidden layer is. But what this hidden layer allows us to do is allows us to do things which get away from Minsky and Papert's objection, because these hidden layers are going to be exactly what we talked about before. They're going to be the Hebb sort of perceptrons with a squashing function. And it turns out that you have to have a nonlinearity in there, because if there's no nonlinearity in there, then it's just a linear operation. You'll notice, for example, just going from the input vector to the inputs of the hidden layer is a matrix vector multiplication. The matrix is all of these weights. The input is a vector corresponding to all of these values, and the output is equal to the matrix vector product. And it does turn out that this is the reason that NVIDIA is really happy in neural networks, is because it does this matrix vector multiplication really, really well. So let's identify some of these things. We have the weights here, and then we have the Z's. Now, it turns out the Z's are the summation of the inputs times the weights. And then the Z's are subjected to the nonlinear sigmoid function, the squashing function. So this generates the so-called state of the neuron. And we talk about this in terms of A. So we put in Z, we run it through the squashing function for each neuron, and the output is A. This A value is what is transmitted to the next layer, if you will. Here's a general. This is a little bit of mathy, but I'll make available on the slides for you because I think it's pretty definable. Let the input be X and define the four layers. Now, it turns out each layer is a function. It actually takes the result of the previous layer and does a function on it. So we can think of it as this f of x, which is equal to function one, function two, function three, function four. So it's a function of a function of a function of a function. Now, the first layer is given by this relationship. W is the set of the weights. B is the bias. Remember, we said um, that we need a bias in order to get things off the origin. You can see here that if you don't have the bias, if X is all zero, then the output's going to be zero. And that's no good because that means that your line has to go through the origin. The bias actually lifts the classifier line off of the origin. So that's what this is. And then we go to the second hidden layer. Now, the second hidden layer is going to have different outputs according to the mathematics behind the neuron. So it's going to have a squashing function applied to this. And then the third layer is going to have another squashing function applied to this. Notice all the squashing functions don't need to be the same. They usually are. And sigma 4 is the same thing. So in each case, a sigma is an activation function like the sigmoid, the hyperbolic tangent, or something like that. The W's are the weight matrices connecting the different hidden layers, and the B sub I are the bias vectors. So if we put these equations into here, we get this result. We get that the output is equal to this blah 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 blah. Okay, and so we have all of these very interesting results. And what do we have to do? Well, we have to find the weights which minimize what we got with what we want. Think about this. This is an enormously high dimensional space, right? Because our variables are W sub 1, that matrix, W3, W2, W1 is an incredibly high dimensional sort of optimization problem. And we have to optimize in accordance to all of these weights. And that's a lot of weights, even in a very simple neural network. So we want to search the weights that minimize the error loss between what you want and what you got. And so that is something that we need to do to train the neural network. Now, this is a search problem, right? We're searching for a solution of the weights in order to minimize minimize the error or the loss function, if you will, between the input and the output. Now, the core idea, noticed by Paul Werbos and later popularized by Romo Hart and some of his clan, is the idea of partial derivatives. If what we want to do is if we want to do steepest descent with respect to all of the weights, we need to take the steepest descent of all of the weights with respect to, I'm sorry, the partial of the weights, partial of the loss function with respect to the weights. That's what we'd like to do. Now, the loss function only lives on the output, okay? The loss function only lives on the output. But we can break this up using partial derivatives. This is equal to, as you can see, if you remember partial derivatives, uh, the partial of L with respect to A sub j with Z sub j. This is the cool one because this is the sigmoid. Remember, we said that the derivative of the sigmoid was actually expressible in terms of the sigmoid. And then we get d sub zj, d weight j. So this is actually the distance downhill for all of the weights, every weight in this layered perceptron. So here's the definition. L is the loss function. A sub j is the activation. What does that mean? That means it's the input to the neuron before the nonlinearity, before you've subjected to the squashing function. And and then Z sub j is equal to the matrix multiplication times the previous layer plus the bias term. And so, oh my gosh, we have a lot of different things to minimize. It's a very high dimensional search space, and we've seen the cursor dimensionality. So here's the expanded form, and this is where the beauty comes in. And the beauty is going to pop out at you in just a minute. First of all, we take the loss function with respect to the individual weights. We expand them in these partial derivatives, and we can look at each one of them individually. Let's look at the rate of change, the partial with z sub j with respect to w. Well, it turns out that's just the input into the ith neuron. So that's kind of cool. The activation function is with respect to z is the derivative of the sigmoid as a function of z sub j. Now, the derivative of the sigmoid, you remember, was the sigmoid times 1 minus the sigmoid. So we don't have to actually do a derivative here because we're judicious and smart in choosing our nonlinearity. We can do this in a very nice way in order to calculate the derivative of the sigmoid function. So what we get if we apply all of these to this top equation, we get the way downhill. Remember, this is the loss function with respect to the ijth weight as equal to delta JL times the activation L minus one. And I'm going to show you why this is so beautiful in a minute. I haven't defined what the delta is. The delta is the delta is given by this relationship. And we'll show what the delta function is and why it's important and why it's very measurable. So now we have error back propagation. Let's talk about error back propagation. We consider a neural network composed of all these parameters. We've seen the parameters before. I've put in the little notation here to just remind us. And we get all of this results, and the final layer produces a prediction of y hat. And then we want to minimize the distance between what we want and what we got. So y is the true target output, y hat is the predicted target, and L is the loss function. And we want to compute the partial of the loss function with respect to the weights for every value of L. And we get the delta L is given by this relationship. And this backpropagation defines the error term for each layer. And this delta L is something which we can compute by error backpropagation. And we do it this way. Let me skip to this slide here. Notice that the neural network is going from left to right, from input to the output. The error backpropagation takes the dells and propagates them from the output back to the input. That's the reason they call it error backpropagation. So we can take the deltas of one layer, we can subject them to the weights, we can sum them up, we can pass them through the derivative of the sigmoid function, and that gives us our next delta. So you can see here that we're backpropagating these deltas, and it's very beautiful math because these deltas are something which can be calculated very easily, and then we can get the next delta to feed into the next layer. And so this idea of error backpropagation is very powerful. Okay, I'm going to go through this a little bit more next time, but I want to get to the punchline here because we're running out of time. Here is the beauty of error backpropagation, and it might not be apparent with the math, but I'll do it here. The derivative of the loss function with respect to W is given by this. You know what this means? This means as we go forward in the neural network, we paint all of the neurons with a Y sub j. As we go backward in the neural networks, we paint all of the neurons with a delta. And then what error backpropagation does is as follows. It says that in order to update this weight, we only need to know, this is important, we only need to know the value of the delta here and the y here. We don't need to know anything else which is happening in the neural network. And that's pretty incredible. We don't need to know what is happening in the rest of the neural network. We can do everything locally. Again, we go forward, and this is kind of a animated GIF showing this. We go forward with the neural network, and then we go backward. The backward is not shown here, but we go forward and we paint all of the neurons with a value of y sub j, and then we go backwards and we paint all of the neurons with a delta sub j. And then we could go back and update each one of the weights with only the information of the two connecting neurons. It isn't Hebb's law, but it has a smack of Hebb's law, right? It has the smack of Hebb's law in the sense that the update is only due to what's happening at the two neurons. It doesn't care what else is happening at the rest of the neurons. It doesn't help the rest of the neural network. We can just have a local sort of thing. So do you see the beauty of that? If we go back to the optimization problem, let me go back to the optimization problem just to make the point. Okay, remember this? This is something we needed to minimize. It's a search for the W's. This is a search for the W's. Do we have to use error backpropagation? No. We could use an evolutionary program. We could get like 50 different values of F, and each one of them has assigned a different value of weights. We could keep the best 25 of the ones, the best that put us closest to the output. We could replicate that, we could mutate that, and then we could go back and perform this operation again. So we could do the evolutionary search. So there's a number of different searches that we could do in order to find the W's. But each of these searches, of which I'm aware, requires you know everything which is happening in the whole neural network. Error backpropagation, on the other hand, is beautiful because in order for it to work, you only have to know what is happening on the two neurons connecting a weight. The weight can be updated only using the two neurons. So that's pretty cool. So that's a thumbnail of error backpropagation. Next time we get together, I'm gonna backtrack a little bit and go over a little bit more in detail what the error backpropagation does. And again, it's beautiful because it just requires local information. In order to do optimization, you just have to know what's happening on the two neurons, one through the forward pass, the other one through the backward pass, and you can perform the update. And it turns out, like anything, it's a steepest descent sort of problem, and it isn't going to get you there on the first step. So you're going to have to go forward and backward and take a step towards the best result. You're going to have to go forward and backward and take a step towards the best result. And many times this takes thousands, lots of different iterations to actually get you downhill to the minimum. So it's a fascinating algorithm. And I think Paul Werbos is to be congratulated on being able to show this. I think it's just genius mathematics, and it's really beautiful if you look at it as through a mathematician's eyes, I guess. Okay, so I think that that's all that I wanted to say today.